her work is very interesting because her work is for the developing and deploying the AI-driven network mechanism. It is called the Hecate. It uses the segment routing. Her result is very interesting. I think you can have a you can be interested in the her work very much. Miriam, is there? Can you connect her? Actually, she cannot hear.
She just replied and said there's sound she can hear now. Just ask her if she can talk.
Can you speak? Miriam? Hello?
Ask her to keep speaking.
Can you speak? Miriam? We cannot hear you. Hello?
Hello.
She's there. Right.
Her voice we're just checking on the audio and fixing
Okay.
it. Sorry.
Hello.
Are
Hello.
you Joel?
Yeah, I'm Jan.
Keep talking.
Okay.
Keep talking.
Hello, can you hear me? Hello. 1, 2, 3. 3, 2, 1. 1, 2, 3, 4. Hello.
Keep talking.
Okay. 1, 2, 3, 3, 2, 1.
Keep
1.
talking.
Okay.
I mean,
Okay, keep talking.
Move away from the speaker.
Yeah.
Move away and keep talking.
1, 2. Okay.
Keep
Wait for me.
talking.
Okay, good. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Hello. Okay. Can you hear me now? Is there?
Can you hear the internal sound?
Not sound.
Inside sound? Can you hear?
Just now I can hear, but I don't. But I think it's inside.
Okay, Miriam, can you
Okay.
hear me? And can you speak, please?
Do I need to still speaking? Uh, 1, 2, 3, 3, 2, 1. Hi. Hello.
Can you try speaking loud? See if it's just very quiet on our end. Miriam, do you have a different microphone that you can try using? Because we had a different person join on Zoom and we could hear them, but we're currently not hearing you.
Uh,
Okay, so yes. You speak again? Oh, that means speak.
Yeah. Hello. Can you hear me? I think can.
Hi, Miriam. If you could please try a different microphone. We're not getting the audio from your side at all at the moment. Oh, she disconnected. Oh, yeah. Excellent. Okay, but we've tested the audio. So we've tested Zoom, we've tested local audio. She can hear us from here because she was then responding. So at the moment, everything here is working. Thing to remember, remote speaker, when they present, it'll of course bring their screen up, take the Zoom over to there, put it up full screen. When we come back and we're doing local presenters, they do their HDMI. What you need to do is you need to put this back to HDMI, picture in picture. Right now it's just on camera. And you need to pin. Yes. Yeah, you see that's the camera view. And you need to pin and spotlight for everyone. Okay. And then make sure it's over on that side. Correct. Yeah. And when they do remote share screen, take off the pin.
And then
Yes, yeah. No, just to. Yeah, because the remote will be in Zoom rather than the input there.
yeah, we will assist.
Perfect. There you go. That's for him. And yeah, if you can't hear Miriam, it's on her side because we've tested with Zoom. Yeah. That's why it's always good to be able to connect and test. It's hard to keep talking when I tell people.
Talking again.
Oh, you need to speak into the.
Hello, Mariam.
No.
Can you try talking again? Yeah. Are you speaking? Oh, we can't hear you. Is there any other microphone that you can use? Maybe you can join. Yeah, you can join via phone also. Oh, she said.
That's Miriam.
Hello? Can you hear me now?
Yes, you can hear.
Okay, good. So, okay, I've joined via my phone, and I'll try to share my screen. Sorry, it's taken long. So, do you still want me to go?
Okay. I'm sorry for the delay. Miriam, the first speaker has access to the Zoom, and her voice was some problem for the connection. Anyway, then she can start the presentation. Miriam, can you start?
Sure. So, thank you, everyone. Sorry for the problems connecting, but hopefully I'll try to run through quick so that we can catch up with time. So thank you again for the very kind invitation to the community. We really enjoy doing these talks, and I learn a lot from your talks as well. So I actually stay till the end. So The work which we've been doing is to integrate AI with network engineering problems. So how can we actually make AI do actions to the network? So one of the problems we've identified is traffic engineering, which we've been trying to build a tool that can be installed. So last time, which was 3 months ago, I presented this idea that we've integrated AI with segment routing, where we did path-aware traffic engineering. We've now taken that work forward to do application aware, and I'm going to show you guys like what we've done and welcome feedback and even collaboration if you are interested. So our goal is to build a truly self-driving network. So my vision is that AI does manage everything and engineers are freed up to do much more interesting tasks. So the talk is divided into two components, the segment routing piece and the machine learning piece. And then I'll talk about the future work, which we are currently working on, where we've introduced these traffic classes to do application-aware routing. So the challenge is to run networks hotter. So as we know, a lot of our networks for wide area and signs are configured to just go up to 40%. Or 60% also. And we intelligently design these networks to have some room in case there are some bursts in the traffic, which we see all the time. But this particular solution is not going to help us in the future because we see an exponential increase in data, especially with AI workflows also coming into the science we do. We also have wireless connections now happening. We're also working on quantum networks, so we don't know how that's going to be impacting our network. So just buying more is not going to be our solution. So what we're thinking is how can we use AI to actually get most of the stuff out of what we have right now so we can use most of it. So looking at science networks and the science traffic we have, a few things come to mind. You want to do high performance throughput with minimum loss. So, or you have time sensitive flows and capacity capping, which I talked about. Then we also have latency sensitive flows. So for example, we're introducing clouds a lot or drones where you can actually put in control APIs and the drones actually go into the field, collect data and come back. So that is another networking problem that has to be latency sensitive as well. So what we've been using in the US or ESNet is advanced reservation systems, which is called OSCARs, which allows you to basically reserve a bandwidth that I'm going to be running an experiment for the next 4 months. And I'm going to be reserving 50% of this pipe so nobody else can use it. So that is how we currently do work. But our idea over here is to make this much more dynamic. Thinking about this, it becomes a combinational optimization problem where not only are you looking at bandwidth, you're also looking at capacity, latency, delay, and maybe there are more metrics that are of interest to the kind of traffic you guys have on your network. So a precap on Hecate is the basic idea that we've been building. So we have a network of 4 routers shown over here. We collect real-time topology, network health, and traffic patterns. That allows us to build a graph representation of the network. So we have node features and edge features all captured here. We can use this information to do link prediction. So we can predict with a certain amount of accuracy a few hours ahead. So you can use that to do some optimization. And you can also feed that into a greedy search algorithm to come up with a discrete routing update and then push that onto the network so the network keeps changing dynamically. So imagine if we have routing tables, you're updating those constantly and it's being optimized. So to prevent loops, you can set this up to do only once a week or once a day. So that it's actually an optimized solution. Otherwise, it does go into loops. So that's why we've been experimenting with this. So in terms of the network health data, we're reading in live NetFlow, Personer, and SNMP data. We're using unsupervised cluster analysis and graph neural networks to do the predictions. And then we're basically just pushing using a global route optimizer. So here you can also use a deep reinforcement learning to find optimal routes and then push them down. So one of the challenges I was having was when I was doing this work, I am a software engineering person. So I was working to identify from a software point of view what can be controlled. I couldn't find a solution by which I could push the commands onto the network because the routing tables are very finite, and obviously updating them is a huge issue. So I teamed up with this team in Brazil, and they have this solution called Polka, which does source routing. So it goes away from traditional table-based routing, and it allows you to add packet labels, which most of you would know. So how P4 does stuff, you add labels to the packet, and then as the packet moves across the network, it keeps popping the first header, and that header tells it which way to go, left or right. So you can actually do a lot of intelligent dynamic movement of the packet through the network. So Polka is released as an open source tool. They've used very intelligent maths like Chinese remainder theorem, and there are some papers over here. So they've already released it, and they're using it in the Brazil network. So I teamed up with them to see how we could use it with Hecate. So this is an example of how the path moves. So you have basically a set of switches put into the flow path. So what it does is, as the packet moves, it looks at the first number. So it's 1, so it knows that I need to go out gate number 1. When it moves to the next one, it knows that the pop is 10, so it goes out to the gate 10, and that's how it reaches the edge or the destination. So what we've done is, last time we merged Polka with Hecate, and all was done through API. So Polka also is written in Python. So what we did was we have the same architecture, topology, network statistics. You collect data. Hecate collects all of this, or Polka can also collect. And then Polka then sends that, which path should I take to Hecate? And Hecate does its AI and machine learning optimization and returns a path and pushes that to Polka. And then Polka basically says, okay, take this path. So that's how the network actions are happening. So that's how the two teams kind of merged. We have a collaborative GitHub repository, which we've open sourced now, where we demonstrate how AI could be merged with adaptive routing over here. And we have a paper which was published last year at SC20 as Indus. So that was an interesting first demonstration of how this is going to be working. And we demonstrated this on a P4 testbed live at SC. So that was pretty interesting. So what we're doing now is that, so just to talk more about these paths, so Polka exposes all the existing paths. So in this particular topology, you can see that there are 3 kind of paths: yellow, red, and green. So Polka reads those in, and it exposes these paths to Hecate, that these are the available paths I have through my endpoints. And it also measures this data. So we've configured it to return to Hecate these kind of data sets: RTT, latency, loss, link occupation, and it can be asked to return more data. So that then comes into Hecate, and then we run it through our optimization or objective functions, and it returns back a path. So the new work which we're doing is we're going away from this path, because this only happens once, where traffic comes in, you allocate a path, and that's it. We're thinking of going much more granular now, that depending on the kind of application flow that comes in, can we select different paths? So I will show you what kind of traffic classes we're thinking of. So I have a research scientist from Georgia Tech, who's George Washington, who's joined us to do this work. So we've identified 7 different kinds of traffic flows that we see in our science network. The first one is long living, which we are very much familiar with. These are long duration, high total bytes being sent with a consistent throughput. And this is usually going on for a few hours. The second one is short living, short duration, and maybe many in number, so small amounts of files being trickled down the network. The third one is low latency, where we have to have high priority, low latency given to these, and low jitter, so there is no loss in these particular traffic kind of flows. Then it's the priority. So say some kind of an important experiment is running, we want to prioritize that particular traffic for critical applications. Then it's the high throughput. So this is just in general, we have like a priority traffic with low drop probability, or medium or high priority with low drop probability. Then the most interesting one is intent. So we've been doing a lot of work on intent. So intent can be a collection of different parameters, kind of like an SLA you give to a network traffic, which is my preference. So for example, I can have an intent that my traffic is not going to go via this particular country. So that could be an intent condition that is part of this traffic, or I could have particular loss or jitter values defined that this is acceptable. So you can do very interesting stuff with intent. So that's a different kind of traffic class. And then our favorite one is the default one. So when nothing works, everything is best effort. So that is what we've come up with, the 7 traffic classes, and we've done some literature review for this. I'm inviting you guys to think about this. If there is something where you think we are missing, feel free to tell us and collaborate with us. We'll be happy to have you on the team. So what we've now done is, because we're adding these 7 traffic classes, now we need to have an edge node classifier. So we are now adding a network flow edge classifier, which will read in the traffic that is coming in, use machine learning to classify this, and then label it that this is traffic class 1, 2, 3, for example. So it's basically doing traffic classification at the edge, and it's attaching a label to it. That label then allows the traffic to be handled by the Hecate optimizer based on what it is seeing. So the next step is that once it is labeled, the Hecate orchestrator now takes that and then finds what the best path for that particular traffic class would be. So that is basically looking at the edge, the core network state, like what is the network looking like in the next few hours. And then it also needs to do some hybrid load balancing to make sure that not one particular traffic class is always getting the best optimized, and there is a lot of waiting in the queues. So we're also looking at how we can optimize the 7 different queues that are now forming. So we're looking at queue algorithms and how that could be optimized. And then eventually this is then worked out like what the best path is. And then we send that information back to Polka, and then Polka selects a different path for each kind of application that comes in. So the whole, so this is some initial results. We are still working on this. So we have an agile migration to a path. So right now we're just showing like 3 different tunnels, and then we are transitioning one particular traffic from one path to another path, which is an optimized path. So the best thing about using Polka is that the switching of the paths actually takes very less time. So it allows us to switch very quickly. So that's good. From a machine learning perspective, we can get immediate reaction. So we're still working on this. And I just wanted to show some initial results. So we've added an edge classifier and a source orchestrator. We also have different objective functions per traffic class that we are now defining. And we are setting up a P4 testing environment at Oak Ridge with Broadcom switches. One of the challenges we're having is we want data sets so that we could train the machine learning classifiers. And if you have data, the community does, then I think this is a great platform that we could start sharing data among each other so that we can actually make progress in this area. And we are currently writing up the paper to appear for SC25. So hopefully I'll have more results by then, but this is the work where it is so far. And thank you.
Thank you. Thank you for presentation. Any question? Actually, I have the one question in the different viewpoint. These days, I'm interested in the end-to-end networking, then do you consider to develop the module to negotiation the policy between the domains? Actually, when I try to QoS enable the communication, we can send some packet across the countries. Then if two countries try to your mechanism to try to deploy the mechanism, and then I think two countries has a different policy for the QoS. Then I think the QoS parameters can be delivered through the BGP between two countries, and then the negotiation part for the QoS is needed. So do you think you can develop those modules for that?
Yes. So what you're describing is a very interesting problem. So right now this work only works with a global optimizer, assuming that Hecate has all the information and does an end-to-end calculation. But eventually I see that what you are saying needs to be done. So I think we will have to add another kind of an optimization, like how it jumps from one domain to the other, because you wouldn't have information from the other domain. So you'll only have one domain where you can do optimization, and then you do the handoff. So I think it's an interesting problem. We can work on that together to see how that would work.
Okay, thank you. Well, okay.
You can stop sharing.
Yeah. So thank you for Miriam for a very interesting presentation. It's good to see your progress. I remember seeing this also some time ago, and you're really moving along with this. That's very nice. How far do you think this is from being something you can put into actual production on, say, the ESNet network or something like that?
So we've been doing testing in our own testbed and proving it again and again. But I think the production networks are still very far from adopting this kind of technology. So yeah, so maybe what they could do is they could assign some kind of bandwidth to us, and we can play within that particular bandwidth across the network. But we've demonstrated this successfully to DOE. So let's see when. So the question is basically when our network provider is going to allow AI to be playing a role on their network. So
right.
it's not just.
And I guess also here, the challenge is to get production networks to deploy source-based routing, right? As much as it's machine learning, right?
Yeah, source-based as well. So even they're doing a lot of testing for just source-based as well.
Yeah.
So I think that's why I've been working with the Brazilian network and some of our own test beds, because they're easier for us to deploy things and test it out.
Yeah. All right. Thanks a lot.
Any further question? Okay, thank you for your presentation.
Thank
please
you.
give your hands. Thank you.
Thank you.
Next speaker is Jelly Meng from China.
Oh, sure, sure, sure. Oh. I don't think I have joined. I don't want to join. I see. Okay, perfect. So thank you for inviting me to deliver this talk here. I'm Zili. I'm from the Hong Kong UST, the University of Science and Technology. So welcome to Hong Kong. The talk today I'm going to present is a network design on the AI-driven, ultra-reliable, low-latency applications. I will tell you more about what these kind of applications are. But the question here we are trying to answer is how we can have a better network design for those AI applications that requires extremely low latency. This actually roots from our research previously in the video streaming. Right? You can imagine like probably like decades ago, video streaming starts the question of how we can have a lower latency on that. Starting from the previous video conferencing, cloud gaming, and some like teleoperation for the robots and also remote surgery, the whole ultra low latency application is emerging. And later we have more, right? For example, we have the AR, VR applications, which requires a lot of interaction between the user and the application. So why this kind of application is actually requiring a lower latency than the previous ones? So this is the research, not by us, but by some like human computer interaction people, the HCI people. They find that the people's sensitivity or human being sensitivity on the latency actually goes up with the angle of view. What does it mean? For example, all of you sitting here, when you are watching the screen in front of you, probably it's like 30 degrees something in your eyes, right? It doesn't take that much in your of the whole view of your eyes. But imagine if you're wearing AI glasses or VR glasses, like the glasses that we are wearing currently, it's going to take up the 180 degrees, so the full panoramic view of your eyes. So in this case, even subtle latency fluctuation will cause to your dizziness, your uncomfortableness, and even your reaction to the stalls. So we need to have a better latency guarantee or latency reliability for these new applications. Oh, by the way, I just want to know, how many of you have tried with the recent AI glasses? Raise your hand. No? Okay. You can try it this year, especially in this year, 2025. There are a lot of new AI glasses in the CES that are like Rocket and even the Google ones, and Meta is trying to propose a new one to replace its previously Ray-Ban. So a lot of new AI glasses are emerging. So for these applications, the first thing we need to do it in a more technical way is we need to know how much reliability we need, right? Imagine now I can see like many of you, including myself, we are wearing glasses all the day. So how long will we typically wear glasses, right? We put on our glasses when we get up from bed, and maybe take it off when we go to bed in the evening. So probably we will like use the glasses for 10 plus hours every day. If imagine in the future, something in the future, you're going to wear the AI glasses, like the typical glasses you're wearing. You also need to wear it for 10 plus hours. And even one single stall, let's say 1 second. 1 second is actually quite long. Even 1 second stall happens every day. That means your glass is going to have a stall every day, which is not very good. So let's just say 1 second. 1 second over 10 plus hours. This actually asks for a reliability of 99.999, so 5 nines%. This is not only for the network itself, this is the end-to-end latency. So from the AI glasses capture your eye motions or your cameras to the time when the new scenes or the new images is refreshed or displayed on your screen. So we need ultra reliable low latency. So here comes the question. For these interactions in the AI glasses, where does the latency come from, right? When we say that we have a stall or I feel a stall, that typically means that the latency has already gone up to very high, let's say 100, 200 milliseconds. Typically, the latency, like you guys can just try to ping google.com here using the edge ROM in this hotel. The RTT for here to google.com probably is only 10 milliseconds or less due to the CDN, due to a lot of acceleration techniques. But for 10 milliseconds, people cannot tell the difference at all. When we are saying like we as a human being, we can feel, we can perceive the stalls that in most of cases should indicate a latency of 100 or even 200 or even higher. So for this difference of like 200 milliseconds or 150 milliseconds, where does the latency come from? This is the internet architecture. I'm sure all of you are very familiar with this. Probably that recalls your memory when you were in the college time. But if you're a teaching network like me, then you are familiar with this every year. This is the application layer. In the application layer, video are actually captured from the camera, encoded using the video encoders like X264, VP8, VP9, this encodec, and then go to transport layer. Transport layer has two roles. One is the rate control, the other is the reliable delivery, right? First, you need to make sure every packet is reliably sent from the sender to the receiver, which means no packet loss, right? If there's a loss, you need to recover from that. And second, you also need to make sure that the sender does not overshoot the network. A lot of protocols here. And later it goes to network layer. So the role of the network layer is resource sharing. For the transport layer, for the application layer, the main role here is, okay, I wanted to make sure that my connection is good. But when we go to the network layer, we need to make sure that I can grab enough resource for my flow when I'm competing with other competing flows. So we have fair queuing, we have a lot of different schedulers on network layer. And later we go to the link layer. Link layer, we also have the channel management. If you can imagine, if you can think in this way, for network layer, actually I'm competing between flows and other flows, right? My flow and other flows. Then for the link layer, actually what is competing here is flows and non-flows, right? I'm competing with the microwave. I'm competing with Bluetooth. I'm competing with a lot of interference and blockage. That's the job in the link layer. I didn't plot the physical layer here because I do not work on physical layer. But for all the other layers, I will tell you where the latency will come out later. And later, when the data packet goes from the server to the client, it will also go all the way up from link layer, network layer, transport layer, and finally to the application layer. So now question, where component or which component in this plot might result in a latency increase of like 100 plus or 200 plus milliseconds, right? We are talking about a delay increase. For the delay, sure, like everyone can think, encoder has delay, network has delay, propagation has delay, and even the transport layer, there are socket buffering delay, a lot of delays, right? Different components. Which part can contribute to the latency increase? So let me tell you the brief answer here, because we have a limited time today. So I'll just tell you the answer. The answer here is no single part can contribute to the 100 millisecond level of delay. Because for codec, they are already optimized for decades from the like image processing, video compression people on the high performance GPU. For here, even you use like FEC, error concealment, it's still very fast. For network, if we are talking about the propagation, right? Even if it's from, I'm seeing, do we have a slide here? Okay. Even if it's from here, Hong Kong to let's say San Francisco, probably 12,000 kilometers, then the propagation delay, considering the speed of light reduction in the fibers, is still like within 100 milliseconds. And remind this from Hong Kong to San Francisco. Most likely your flow, your traffic is only from Hong Kong to at most Singapore, right? So the answer is the delay stays in the buffer between the components. This includes a lot of buffers here, actually. Okay, we just skip this. Why we need to have a buffer between the components? The reason here is because video codec network in the transport layer protocol stack and on the routers and on the link, they are all different asynchronous components, right? Codec people develop a codec, and the network router, there are a lot of routers one by one. they are asynchronous. For wireless, there are drivers, there are firmware, there are different components as well. And for protocol stack, that's maintained by the network people. So different people maintain different component. Then how to hand over data from one component to the other? We need a buffer in between. So the upstream component, after finish processing the data, they will put data into the buffer. And the downstream component will pull the data or fetch the data from the buffer. So then we have a buffer. And why the buffer latency matters? This is because the network latency, especially for the wireless network capacity, it is always fluctuating. So this was a measurement from 2022 from our group, where we measure the Ethernet capacity with a lot of different wireless network, including Wi-Fi in the restaurant, in campus, in the office, and also 4G, 5G. So different traces represent different wireless network types. What did we measure? We measure the network bandwidth at a very fine granularity, namely every 200 milliseconds. We measure the bandwidth. Every 200 milliseconds, we measure the bandwidth. And we calculate the ratio of two adjacent network bandwidths. We can find that for the wire network, the network bandwidth does not change that much. So this means that at the top 1 percentile, how the bandwidth will fluctuate. And for the wire network, at the top 1 percentile, the bandwidth will only fluctuate at most by a half, right? It doesn't fluctuate that much. But for the wireless network, the bandwidth can be reduced by a factor of 6 to a factor of 50 just in 200 milliseconds. So this is a huge fluctuation. And this is something out of our control, right? This is due to the interference, blockage, and competition. But the key point here is we need to make sure the application, let's say AI glasses, can quickly adapt to this fluctuation, right? It's easy to adapt. We just reduce the resolution. When the capacity rate goes down, we reduce the bit rate, we reduce the bandwidth, we reduce the video codec parameter. Then we can quickly have a video frame or a video stream that match the current capacity. But how? How does it work? The mechanism here is called the back pressure. So each time when the downstream capacity goes down, let's say it's reduced by a factor of K, the upstream component knows nothing about that because they are asynchronous. There are no information exchange between that. So what they will usually observe is the upstream bit rate first has a reaction time. Let's say it observe the buffer goes up, the buffer is gradually built up. And when the buffer is high enough, they realize that, okay, probably I should reduce the sending bit rate or my bit rate as well. And then it goes down. So there must be a reaction time in the current interaction between the components. But the problem here is that, let's say this reaction time is tau. All the packets you are sending at this time, they are overshooting the network. They're sending much more than the network can absorb, which means they will take much longer to be drained or to be cleared up. So let's say you only take 100 milliseconds to react, but the bandwidth goes down by a factor of 10. Then how long will this packets be drained up? It will take 100 milliseconds multiplied by 10 times, which is 1 second. And during all this time, users will experience a lags. So what we have done in the past, probably 7 and 8 years, is just trying to mitigate the buffering delay between every component. I list some papers here from our group, so you can, if you want to know more on the details, you can just try to find me later offline, or you just Google the paper. First, originally we thought, okay, probably we can just try to make a better prediction on the rate control. So in 2018, 2019, we start to use the AI techniques. At that time, that was not even LLM. That was the deep reinforcement learning. We was trying to use that to predict the bit rate, to make the bit rate more robust and more predictive so that it can sense the network changes. Later we found that it doesn't work, right? So we go to the buffer between the transport layer and the application layer. So what is the buffer here? The buffer in the transport layer, if it is TCP, this is actually the socket buffer, right? Each time you write the application, you use the TCP socket. How does it work? How to send a packet in the TCP socket? You write socket.send and copy a buffer space from the current buffer space to the kernel buffer space. But you do not know what is happening after that. You copy that, that's no problem. But when the data goes into the socket buffer, it might also be queued and be waiting for the sending opportunity controlled by the consensus control. So this delay might also go up. So we have a work in the CCOM last year, which also got the student research competition gold medal, which tries to reduce the buffering delay for the TCP socket buffer. And later in this year, we also have another work in CCOM, which tries to control the latency of the pacing buffer from a lot of AI or RTC-driven applications. For the network layer, we also need to manage the buffer on the routers. So for the routers buffer management, we also have the issue of the back pressure, right? How does the upstream router know that its downstream capacity is going down? For data center, this is easy. We have a lot of techniques like PFC or any link layer techniques to solve that. But for internet, this doesn't exist. So how can we know that? So we have a lot of tricks in trying to perceive or try to carry this information onto the existing flows without modifying the protocol. To try to let the routers tell this upstream, especially the center, that the router capacity is going down. Also for the receiver side the transport layer has the buffer is also the socket buffer. But for the row is a little bit different. For the center side, the role of the socket buffer is to avoid sending too much, more than the determined by the consensus control. For the receiver side, the socket buffer is going to reorder the packets in case there are any out of order ones due to the network outage. If you have received packet 1, 3, 4, 5, you cannot send it to the application because packet 2 is missing. This is called head of line blocking. You need to wait for the packet 2 coming again to send them back. But during this time, buffer also goes up. So we have some techniques here trying to control this buffer and to coordinate this with the sender. Sorry. Later it goes to the decoder. Before the decoder, there are also buffers before that. What if the decoder cannot decode fast enough? If the decoder cannot decode fast enough, the video frames or any data frames will just wait before the application, right? The application cannot fetch. If the application cannot fetch data fast enough, then the data has to wait before the application, which is also kind of buffer. We also have a work that just got accepted on SDI this next year, actually, is to manage the buffer on the Wi-Fi protocol. So namely the 802.11 protocols. We modify the firmware, we modify the driver, we modify the kernel modules to make sure that the Wi-Fi router can provide an upper bounded latency. And the solution or our answer to that is we achieve that by coordinating all the buffers inside the driver, inside the hardware, inside the firmware, and inside of the kernel modules. So one important thing that I want to point out is that all the works that I presented here, actually, they do not require the coordination between two components. Even if you can see I put a lot of arrows here. We want to make sure that this is 100% compatible with the current protocols. So that, for example, for the router management, you only need to modify the router. You do not need to modify the sender or the receiver at all. In that case, you can deploy on router individually and see the performance improvement. Also for Wi-Fi and the receive set socket buffer and so on. So this is a very brief overview of what we are trying to solve to reduce the latency for those AI glasses in the probably the past 7 or 8 years. We do not have time to go into the details, but if you have any questions, I'm very happy to answer. So the key takeaway here is that we want to coordinate two asynchronous components from the end-to-end delivery pipeline of all these ultra-low latency applications so that the buffer between every two components are under control. All right, that's it. So thank you for your listening and happy to take any questions. Yes. That is a very good question. So actually, let me go back to this picture. Actually, a lot of things we are trying to solve there here somehow bridge the vulnerability or actually amplify the vulnerability of the networks. For example, we are using some side channel information to piggyback the network conditions to the original sender. So the good thing here is that since we are compliant with the existing, like say TCP, RTP, QUIC protocols, so we assume our additional information should not be worse than the existing protocol's definition, right? The vulnerability of protocol is one thing which we do not touch, but which we will not increase the vulnerability for that, because other thing we modify here, it doesn't change the packet structure, it doesn't change the data patterns, it doesn't change the traffic patterns. So from the attacker's view, probably they are kind of same. Probably not, but I think they are the same. So what do we do here? We just to piggyback the information into, for example, here we are doing here is changing the interval between the ACK packets to let this be a signal to the sender and let the sender know more about the network conditions. So for this, I guess only senders can know what this means.
I have a question.
Yes.
Actually, it is very interesting. Then you are assuming the classes. Then I think in the metaverse, some user can see in direction, but abruptly change the direction.
Right.
Then the all content should be weighted in the somewhere. But I don't think all contents can be weighted. So how can you resolve that problem?
Oh, that's a very good point. This is really something like beyond the application, so we didn't touch that much. So for example, when you change the directions of your head, or you move, you walk around, the render content should be accordingly changed based on your new position, right? So this is more in the technique of, let's say, the rendering applications like developed by Meta, developed by the glass vendors. So what we are trying to do is we are trying to make sure the control loop between your head motion to the new display images, the control loop between this is under control. This is upper bounded by all of these buffer managements, so that as long as the control loop is acceptable, let's say 100 milliseconds from end to end, then the new content can be rendered or not is fully the responsibility of the application, no longer the network. That is our main focus or our ultimate goal of this project.
Thank you. Any other question?
Thank you so much.
The cash. Next speaker will be remote. From Japan. Next speaker is Takaya Miyazawa from NIST. His title is AI-assisted time series data analytics for network operation automation.
Okay. Hi, my name is Takaya Miyazawa from NIC. Can you hear me?
Yeah.
Oh, okay. Yeah. Then, okay, so I'll turn off the video and share my screen. Okay. Right. So can you see my slide?
Yeah. It can be seen. It is been.
Okay. So yeah, can I start?
Yeah. You can.
Okay. Yeah. So yeah, thank you very much. And the title is AI-assisted time series data analytics for network operation automation. All right. So yeah, this is the outline of this talk. At first, I'm going to introduce the background of network operation automation. Then I'm going to introduce several existing machine learning algorithms for time series data analytics. And then I'm going to introduce our previous researches, which are distributed adaptive algorithm selection and instantiation, and pedestrian flow analytics for mobile system. And finally, a conclusion. So TM forum defines automation level for network operations, and the current level is 3, and level 4 automation will be required for beyond 5G era. And automation will be indispensable for future network operations because it is estimated that the number of network operators will drastically decrease. And another reason is that more agility of network operations will be required for responding to dynamically changing network cloud environments where application services will be diverse in the future. So this is a framework of a network operation automation utilizing AI and ML, which is compliant with ITU-T Y.3177. And in this framework, the network traffic or server workload data are analyzed and predicted in the process of data analytics, and resource control, including arbitration and or migration, is executed based on the data analytics results in the process of resource and control decision. And utilizing AI and ML is essential because it is too difficult for humans to predict the time-varying network traffic and server workload. And next, I'm going to briefly introduce several existing ML algorithms for time series data analytics. Okay, so first, if we select machine learning algorithms for some data analytics, we need to consider what the most important performance metric is. For example, a low prediction error, a short training time, and so on. And generally, there is a trade-off between multiple performance metrics. So suitable machine learning algorithms is different depending on the objective of the data analytics, the preference in the data analytics, the current situations of network components, and so on. In some, there is no ML algorithm that is the best for any cases. And this time, I'm going to introduce 3 ML algorithms which have widely been utilized in many research fields. The first algorithm is support vector regressions, SVR. This is suitable to predict the data per second because it automatically obtains a regression curve as the predicted data by analyzing the past data. The characteristic of this algorithm is high-speed prediction in less than 1 second. The second algorithm is LSTM, long short-term memory. This is a kind of time series deep learning. This is suitable to predict data, per second, as in the case of SVR, but LSTM takes a long time for training process, but can achieve a higher prediction accuracy than SVR due to the benefit of a deep neural network. The third algorithm is a lasso. This may not be suitable to predict data per second, but suitable to predict the peak value of CPU usage server workload by applying a lasso to multiple regression. The lasso can achieve a high accuracy of predicting the peak value with a small number of memories because it has a characteristic of automatically simplifying the mathematical model for data analytics. So next, I'm going to introduce our previous researches, distributed adaptive algorithm selection and instantiation for a large-scale core network, and pedestrian flow analytics for mobile system. So this is the first one of our previous researches on distributed deployment of ML engines and adaptive selection and instantiation of ML algorithm. We focused on a server workload of in-network functions as time-varying data. At first, multiple subnetworks are interconnected with each other, and one ML engine is deployed in each subnetwork. And there is a central ML repository server which is connected to every ML engine. And the ML repository server manages a table including several elements. The first element is a network name. And the second element is the objective of data analytics, such as prediction of CPU usage per second, a prediction of the peak value of CPU usage, and so on. The third element is the preference of data analytics. For example, a lowered prediction error, shortened training time, and so on. The fourth element is the possible machine learning algorithm suitable for the objective and preference of data analytics. And the fifth element is the prediction error obtained as the data analytics result utilizing the selected ML algorithm. The last element is the training time when using the selected algorithm. All of the information is collected from all ML engines to the ML repository server. For example, a subnetwork needs to run a network function for the first time, and the corresponding AI ML engine needs to obtain the ML information and its source code, which is suitable for the objective and preference of workload prediction. In such a case, the ML engine requests the information and source code to the ML repository server. Once receiving the request, the ML repository server sends the source code of a suitable ML algorithm to the engine. Once receiving the source code, the ML engine automatically upgrades the ML algorithms for the combination of network function, objective, and preference of data analytics. In this way, our proposed method realizes distributed deployment of ML engines for multiple subnetworks and adaptive upgrading of ML algorithms in each ML engines. So this is the second one of our previous researches on predicting the time-varying mobile terminals in each base station coverage area in radio access networks. The objective of this study is to reduce the power consumption of open RAN base stations in terrestrial network while maintaining the quality of services for mobile users. Our approach is to utilize pedestrian flow analytics and the capacity of non-terrestrial networks such as satellite or HARP. So I'm not going to explain the details of this research, but briefly explain the pedestrian flow analytics utilizing AI and ML. The pedestrian flow means the number of mobile terminals in each coverage area, which is time-varying. And the pedestrian flow data is analyzed and predicted for a specific future period by training a machine learning model using the past datasets. So we have used real datasets of pedestrian flow in Kogane, Tokyo City, Japan. As I explained in the previous page, the pedestrian flow means the number of mobile terminals, which is time varying every 15 minutes in each coverage area. And we have used LSTM that I explained earlier, which is kind of deep learning for time series data analytics. We obtained predicted values in 1 day by training the deep learning model using the datasets in the past 2 months. And the right graph shows an example of predicted and measured data. We can see that LSTM can predict the pedestrian flow in a mobile network with high accuracy. So we have also quantitatively compared the prediction error of several methods in the pedestrian flow data analytics. We used real datasets of 2 geographical areas, and One city in Tokyo and Shinjuku World in Tokyo. Japan, and we evaluated the performances of FBS, SVR, and LSTM. SVR stands for average value selection, which is not applying any ML machine learning algorithm. And SVR is a kind of SVR, which stands for least squares support vector regression. This is a kind of extension of the SVR, the typical SVR. The third method is LSTM. And as you can see, LSTM can achieve the lowest prediction error in the pedestrian flow data analytics due to the benefit of the deep neural network. For more details, please see the paper shown here. So in future work, it might be possible to combine the two previous researches that I introduced earlier, which are distributed and adaptive algorithm selection and station, and pedestrian flow prediction for a mobile system. As illustrated here, for example, multiple controllers called non-real-time, non-RT rigs located in multiple geographical areas could be interworked with each other, and ML algorithm installed inside each controller could be adaptively upgraded. Yeah, I think that will be future work. Okay, so finally, a conclusion. There will be diverse service requirements, and the network traffic workload will be time varying in future network. So we need to automate and achieve agility of time series data analytics. AI ML is effective depending on the data sets and objective and preference of data analytics. And I introduced several existing ML algorithms, SVR, LASSO, LSTM, and so on. And I also introduced our two previous researches on utilizing ML algorithms for time series data analytics. Yeah, so thank you very much.
Hello, Doctor.
Yes.
I finished. It's difficult to hear you. Hello?
Hello?
Yeah, I finished.
Yes, yeah. Thank you very much. Yeah. Also, the voice quality was very bad now.
The voice volume is very low, so it is too difficult to hear you.
Okay. Sorry about that. I think that is due to the network environment in my home. Yeah, sorry about that.
Anyway, then, any question? Actually, you have suggested to select some good ML algorithm. Then do you think the the performance of the ML algorithms can be changed according to the some situations? Then I mean in the real time, the performance can be changed according to the situation, right?
Yes, I think the first high-speed upgrading or ML algorithm is one of the research issues. So yeah, I think we need to make the upgrading as fast as possible. Yeah, but I think right now I think it takes around let's say 10 seconds or longer. So yeah, we need to shorten the processing time of upgrading.
And I think the predicting the best performance ML algorithm could be very difficult. Then I guess if you use some digital twin, like digital twin or something like that, those kind of technology, then it could be more useful. Don't you think so?
Yeah, I think that we aim to, create some methods which can which can do autonomous distributed ML, methods. Yeah, so that is one of the our research issues. So I think there could be several ways to select and adaptively select ML algorithms. So I think that will be uh, very important research topics, yeah, in the future work. Yeah, thank you very much.
Do you have do you have any plan to adapt your the selection method to your the real network or some education and research network?
Yeah, actually, this slide shows the one of the approaches, our approaches, which had already been published in NOMS international conference. But actually, this method requires a centralized server, which may not which may not be suitable for real-time processing. So maybe there will be a more efficient method to achieve real-time processing of the ML selections or something. So that it will be a future work.
No, actually, you have a sort of the research network in Japan. So in the next time, if you can deploy your method to your real network and show the experimental result in the next time, it could be very good for our working group.
Oh yeah, thank you very much. Actually, this research has been demonstrated on the NICT's JGN testbed. Yeah, so yeah, but yeah. Of course, we will have to do more researches by use of real networks. Yeah, thank you very much.
Thank you very much. Thank you for your presentation. Give me a big hands, please. Thank you.
Thank you very much.
Next speaker is from China. Is Baojun Liu, Professor Baojun Liu from Tsinghua University. His title is a deep dive into email delivery failures from a large email service provider.
Thank you.
Yeah, please start.
So which screen should I share? Yeah, I really, you mean I should share your desktop? Step desktop.
Where is your presentation?
This one. Oh, sorry, I didn't have shit. Let me check it.
Wow. What is the name of your presentation?
My name is Paul. This is audience.
So this one doesn't work.
It's supposed to be working.
Mhm.
Oh, the adapter is
Okay.
not.
Probably no, probably it's
Yeah,
working now.
it's not working.
Oh, no, no, that,
This is from my feedback.
yes.
Oh, this is no, this is that.
Yeah, this is my screen. It's working.
Can you try the same thing?
Yeah.
Okay. That's
Okay,
fine.
finally it works. Thank you. See. So I noticed that according to the schedule of this workshop, the time is very limited for me. Okay, I will quickly briefly introduce my work. The title is Bonds is Wide, a deep dive into the email delivery failures from a larger email service provider. I'm Baojun Liu from Tsinghua University. I will introduce our team's measurement study on email deliverability and the bonds reasons. So as we all know, email is an important online communication method for daily work and company business. For example, when we sign up for account for communication with our partner or identify authentication or update pushes, we need to send or receive emails. Nowadays, according to the public report, email users has more than 4 billion. However, email deliverers does not always succeed. Email may encounter many types of bounces, such as server misconfiguration and invalid email addresses. Some reasons of email bounces are noticeable to the users, while some are not. For example, if the outgoing server has a poor reputation, our email service provider will help us to resend the email many times, but we don't know about the detail. In the email community, many users are confused about email bounces. For example, people said that many emails was bounced abnormally, but I don't understand the reasons for the bounce, and I don't know how to solve this kind of problem. So what happened to an email during the delivery process? We define 3 status. First, if the email first delivery success, we call it non-bounces. The second is first delivery failed, but the second after retries, which we called soft bounces. The third is that even after many tries, the email is still deliver fails, which we call hard bounces. As for users, we may notice about hard bounces, but what is the status of email delivery in the real world? What are the reasons for the bounces? These are the bulk questions what we want to answer in this work. Before diving into our details of this work, let me briefly outline the email delivery process. The senders transmit the email to the outgoing server, and then the outgoing server sends the email into the incoming server. If delivery is successful, the incoming server responds with OK. However, when email delivery fails, the incoming server returns a non-delivery report message to inform the reasons for the bounce. For example, the email account does not exist. Therefore, we can understand the potential bounces reasons of emails from the non-delivery report messages. Our work faces 2 challenges. First, how to obtain a dead set of a non-delivery report message. We believe that we cannot actively send email messages in the real world because a large number of emails may be potential introduce ethical problems. And it also may not reflect the actual email business in the real world. To address this challenge, we announced the global email delivery logs from Cormail. Commail is the largest email service provider in China. Commail uses a distributed delivery process to send email. When delivery fails, it randomly selected another server to retry. The outgoing server is located in 6 countries. We collected the outgoing server, use each email delivery and the corresponding delivery result. Our data set does not involve cases of received email, and we did not collect any email subject and content. In total, in this data set, we announced 300 million email delivered over the 15 months. The data set included 3 million receivers and 600,000 incoming servers, distributed across 141 countries. As we can see in the geographical distribution map, the blue heat map is the incoming server distribution. Now we have the non-delivery report message data set, but we find that many messages have inconsistent format and means. So the second challenge is that how to identify the types of many non-delivery report message. Our solution is to build a non-delivery report messages classifier based on the BERT, the language model. The construction process has 3 steps. The first, we cluster a non-delivery report message into 10,000 templates. And the second, we manually announce the top 200 template, and we divided the bounces reasons into 16 types. This table in the types, we have defined. At last, we train the classifier and predict all non-delivery report message. The accuracy rate of the classifier can reach 92%. Now, let me share our findings. We found that 24 million emails are soft bounced. 24 million emails are soft bounced. Their delivery success after retries. The amount of this kind of email account for 8% in the real world, 8% in the real world. In addition, 40 million emails are hard bounced. Their delivery failed finally, accounting for 4% in the real world. This figure shows the details of the number of emails delivered by the Commail every day, as well as the number of hard bounced and soft bounced emails. From Monday to Friday, the number of email deliveries held. In addition, we also summarize 5 root causes of email bounces that is hard in the real world, including malicious email behavior and spam blocking process, server manager misconfiguration, and improper user operations. And the last one is poor email infrastructure. If you want to know the more details, please check our paper on my homepage. And then I will introduce the main reasons of our soft bounces and hard bounces. We observe that 10 million emails are soft bounced due to the poor reputation of outgoing servers. It's amazing. An example of the non-delivery report message is server unreachable. Client host blocked user spam house. Spam house is very popular, the email block list that's in the real world. And we can learn that the non-delivery report message which blocks the block list that outgoing server has been included in the history, and which domain adopts block lists such as a spam house. The result shows that 300,000 domain adopts spam house blacklist in the real world, including many larger providers such as Outlook and Yahoo. This figure shows that the number of Commail outgoing server and outbound email blocked by spam house blacklist. It's amazing. And we also noticed that removing the host from the block list is not very easy. It's not always very easy. And it may be not very timely. Therefore, when the outgoing server is included in the spam house block list, the email is sent will be affected. The Bower result highlighted that the importance of maintaining a good reputation for email servers, especially for the outgoing server that are responsible for the email delivery of many users. The main reason for hot boxes is user typos. We find that in the real world, 2 million email delivery failed due to the domain and the username typos in receiving addresses. The most common type is missing some letters. In addition, we find that many user addresses with significant value that can be quoted. Yeah, the details can be found also in the paper. In addition, we also noticed that some malicious activities in the email delivery process in the real world. For example, we find that non-delivery report message associated with some senders or IP addresses are likely email addresses that not exist. This included that attacker maybe is guessing some users' email addresses in the real world, and attackers focus on specific user or specific organizations. Yeah, it may be component some other social engineering, such as phishing, to create many email addresses and manipulate the username for special strings. Also, we can also evaluate the protocol implementations from the perspective of email delivery. We find that non-delivery report message can indicate that verifying support and the deployment of DKIM, SPF, and DMARC is kind of sense. Of course, there are some many others or reasons for email bounces. For example, email contents may be detected as spam. Users get too much emails, and some mailboxes are full, or maybe the email address is inactive. This kind of reasons may also affect the delivery process. Network quality also affected email deliverability. We find that many countries that send to Africa countries are bounced due to the SMTP session timeout. It's very surprising. In conclusion, our study provides a landscape, a management study for the global email delivery. And we evaluate the security process deployment and the users' real user behavior from the email bounce perspective. We also explore the root causes of email bounce in the world. We also provide some insights for the communication and to improve the email ecosystems. We notice that the email community should improve the delivery status in the real world. Okay, that's all. Thank you for listening. Any question?
Any question? Actually, I have a different question. I think all of us have experienced the spam filtering. Then the proper emails can be categorized as the spam emails, and then many of our emails are filtered out. Then we cannot receive it properly. Then do you think any proper method to categorize the emails properly, to handle them?
A very good question. In my view, I think the email service provider should devote more effort in this process. They should maybe propose some tools or some detect services for users, and to improve the email communication in the real world. For the end users, such as me, actually, I can do little, maybe a very little effort in this process. So as a result, the email service provider may be important in this process.
Actually, some email service provider can be just a university or some other non-profit organization. So they don't have the proper solution, or they cannot buy a good solution.
Yeah.
And I think good open solution could be better for those kind of organizations?
You mean open source this kind of you mean open source solution? Yeah, yeah. I agree.
Okay.
Thank you.
Oh, okay.
Thank you. As far as I know, I don't know any widely deployed protocol that can be used in this process. I don't know. As far as I know now, there's no widely deployed protocol to solve these problems. So as a result, in this study, we only focus on the bounces email, and we announce the reasons from the bounces email. It is also a main challenges in this study. I hope in the future, maybe we can propose a protocol that can be defined the different kind of bounces reasons in the world. Maybe the ITF, such as this kind of organization should propose and should implement this kind of protocol. Okay.
And what about the ISPs? Like, do you think that some ISPs have higher failure rates as compared to other ISPs?
In my opinion, I don't think ISP has a responsibility in this process. I think email service provider should devote more effort, more effort in this process. Yeah.
Thank you.
Thank
so
you.
much.
Any further question? Thank you for your presentation.
Thank you.
Thank you. Giving big thanks. Actually, our slide files are uploaded to the OV platform. You can get all contents from the OV platform. Thank you for join our session. Now is the time virtual work. So this session ends now. Thank you. Thank you for your participation. Thank you.